嗨，现在同学听得到我的声音吗？
听得到。
哦，谢谢。看得到我荧幕画面的话，如果没看到的话，也告诉我一下。
看得到，看得到。
谢谢。好，录影了，所以好，我今天尝试了一个非常新奇的东西，所以造成了一些问题。就是我现在使用的是 AirPlay，而且看起来好像不用网络也可以 AirPlay，而且这个好处在于什么呢？在于现在我的 user interface 你们会看不到，所以我这边放大字体写字你们看不到，所以这样你们就不会被我的那个放大这样子啊跳来跳去跳来跳去。我这研究蛮久的，对，不过也是因为这样，所以就造成 setting 的问题，就晚了10分钟。I'm sorry for that. Just saying that I try a lot of stuff, try to connect my iPad to Mac, and I found a way that I can use presentation mode that can hide the user interface. So you won't see I select the color of pen or magnify the words. So you can enjoy nice writing on the projector and also the online. So I guess I can. It is worth to do that. All right, so let's continue our lecture. The last time we talked about the particle in the box. Okay, particle in the box, and we found that when the particle traveling in the box in the one-dimensional, and you can see that the probability you found the particle is not actually uniform. It's not uniform. It actually depending on the energy. If the energy has like low level of the energy, you can find that you have more possibility, higher possibility to find that in the middle. And if you have this next level, you will have other two high possibility area. So which indicate that the small particle motion related to the waves. So hey, hi, students online, please mute. Thank you. All right. So then we need to find out how to dealing with the Schrödinger equations, and we need to find the antinode for the lambda. Well, so lambda is related to the antinode, so we can see that how the lambda is actually equal to 1 over nj equal to 2 times 2l. Okay, and then we substitute the equation, we get one direction px. The p is momentum. The momentum px is equal to the nx times h over 2l, only one dimensional, but we have y and z, three directions in total. And because they are all components, so we need to do it in vector forms. So we need to do the square sum, all right? And then we can get this. The nj has a specific formulation. mj squared equal to the vector sums for each number. So the number called quantum numbers, all right? So last time we talked about this, we stop here, and then we can continue our lecture. Okay, so now we talk about energy level. Momentum can relate it to the energy, of course. As you can see, energy is half mv squared, which is equal to p squared over 2m, because p is equal to mv, right? So you can get the P squared over 2m. So the kinetic energy after we substitute here, we can have mj square h square aml square equal to mj square uh, 8m h square v minus over 2 over 3. Okay, so you can see that the L here is the length of the box, right? So you can substitute the volume, substitute the L by the volume, because volume equal to L cubic, right? So we can make this L become V2 minus 2 over 3. So I guess you can see that it's okay for you. Right. So you can see that the epsilon here, epsilon j, is proportional to mj squared, no problem. And of course, proportional to v2 minus 2 over 3. So which means that when volume decrease, your energy J will increase. Okay, so that's how you can correlate them. Okay, so and this one, these two relationship, this relationship we will use that later. All right, so be careful about this. Keep that in mind, and also we can continue to examine how many possibilities for each energy level. You can see the lowest energy level is J equal to 1. So which means that X and Y and Z direction are all in this style, okay, this energy form. All right, so NX, NY, NZ are all 1, which means that in this case, X looks like this, and Y and Z, they are all look like this. Copy, paste, paste. Okay, beautiful. Right. So in this case, X, Y, and Z are all in the lowest level. So the lowest level is non-degenerate, right? Only one choose, one choice. J1 equal to G1 equal to 1. So N1 square equal to the summation square sum. So equal to 3. So epsilon 1, after substitute that, it would become epsilon 1. So you can specifically determine the value of epsilon 1. And next, we have the next level J equal to 2 is one of them will be 2. So it could be 211, 121, and 112. Okay, so it looks like copy, paste. So you can see that X and for this one, X, Y are in one with the one antinode, but the second will have. Oh, can I do that? Okay. So for this, you can have. That's weird. Okay, anyway. Okay, so you can see that, right? So everything become reasonable. 112 is X, Y, and Z with the X, Y in the first mode, and Z is the second mode. X, Y, and Z are distinguishable, of course. So 2 squared plus 1 equal to 6, right? So epsilon 2 is this one, right? Oh, good. Okay, so now you can specify epsilon 1, epsilon 2, and epsilon 3 based just by your hand, right? Or everyone can do that. Okay, so only specific value of epsilon j are allowed. What does that mean? Which means that energy are quantized, right? So not continuous. Only certain value of the epsilon exist. OK， 好，那么讲的是能量阶。那我们前面讲到P 可以用 lambda 还有 h 来写来表示。那我们现在 kinetic energy epsilon 是1/2 mv 平方。那 P 是 mv 嘛，对不对？哈 ，momentum 啊，那所以说epsilon 跟 P 的关系就是 P 平方除以2m，这应该大家没有问题。那我们接下来就可以把 kinetic energy 算出来，代入刚刚的式子，就可以写成这样一个复杂的东西。那这边别忘了，这 L 其实它的是 box 的长度，然后3次方就是体积嘛，好，所以我们把它写成体积的负3分之2次方。那你可以看到 epsilon j 就会跟 nj 平方成正比，当然也跟 v 这个东西成正比。那也就是说 v 越小，因为它是负的嘛，哈 ，v 越小 epsilon j 就越大。OK， 然后呢，我们就可以一个一个去检视 epsilon 1、epsilon 2它到底长什么样子，或者是什么样的值。我们最低的话，当然就是大家 x、y 3个方向都是第一阶，好，第一个最低的振动模态。所以就是那就是 n 等于1，那就可以得到代入以后就可以得到这个式子。那如果是下一个 level 的话，就是112，好，那当然也可以是211，也可以是121。那这样它就会有3个 degeneracy，OK？ 那 epsilon 2的能量呢，代入进去的话就可以得到这样的式子。OK， 我们可以发现 epsilon 1、epsilon 2它都有固定或是不连续的值。OK， 那这就是quantum mechanics 里面的一个很重要，就是 energy 是不连续的。All right, so after that, we can specify this. We just done the n1, n2, n3 was 111 is j equal to 1, and the degeneracy is non-degeneracy, but actually the degeneracy is 1, right? Because the lowest the level. And this next level is 112 or 121, 211, degeneracy is 3. And yeah, you can imagine that after that, everything become here become more degenerate, and the j equal to 5, which means that 222 again is non-degenerate as well. So still don't know how to use that. Okay, not familiar with this. G phi equal to 1. Okay, right. So now you can calculate by yourself for all the level, and you can get the energy value. All right. So yeah. 所以我们就用前面的方法，你就可以把这个所有的能阶都推出来啊。那大家回去可以试试看。那这边要注意的是 degeneracy， 它的 none 的意思不是说 G1 等于0哦，它是 G1 等于1，好，它是只是说没有别的选择而已。那你应该说没有别的选择，就只有一种选择这样的意思。Okay, next let's calculate the quantum number. So how large of the quantum number is? We want to find a quantum number Nj of 1 liter helium gas at room temperature. Okay, so let's take a look. How large is the quantum number? We assume that it's large, but how large? We want to see it. So in this case, m equal to this one. We can check on the internet, Google it. Then h bar. Okay, h bar is another symbol, but actually is the h divided by 2 pi. So basically, they have the same meaning, but just different different values. But they are exactly the same. Okay. So just take a look. H bar equal to this one, and your epsilon j. Yeah, this is really ugly. So yeah, you can see the h bar h square become h bar square with the pi square. So basically just interchange the symbol. Not big deal. Okay, so let's estimate what is quantum number. Quantum number here. You can see that here this is epsilon j, right? The purpose of this, the purpose of this questions is to determine nj, right? So you need to calculate using this equation. If you have make the right hand side to the left, and then you can get nj squared, right? So now here, this one is the double curve, double wavy symbol. And one thing I need to correct here is that the V here is capital. Sorry, I should change this. As you can see, this is V, capital V, and here should be V, capital V as well. Okay, so if we substitute all these, you can get the double wavy symbol value is blah, 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 blah. Okay, 5 times 10 to minus 21 electron volt. At room temperature, the mean kinetic energy, then here we need to calculate epsilon j. The epsilon j here, epsilon j equal to 3/2 kT, right? And the epsilon is the only single wavy symbol. Then, which is equal to 1.5, 1.3 A times 10 to 23 minus 23 times 293 and equal to 6.06 times 10 to minus 21 joule. It's approximately 3.6 A times 10 to minus 2 electron volts. Okay, so epsilon j looks like this. So now we have single wavy number and double wavy number, and we can divide them together and do the square root, and you can get nj. The nj looks really, really big, 2.7 times 10 to 9. Wow, this is a really large number. So which means that quantum number like M1, N2, and 3, they are really, really big, really, really big. Okay, so yeah, this one shows that the quantum number is really big, so it can help us to determine something later. Okay, it's really helpful. This assumption is really helpful for our next page. 好，我们接下来刚刚不是做了什么 N1、N2、N3，然后我们想要看看这个 N1、N2、N3 到底是有多少？好，到底是有多少？这值是多少？那在一般的状况下，那所以我们去找 quantum number 在1公升的 helium 里面的在室温下。好，那我们要怎么样算这个NJ 平方呢？很简单嘛，哈，就是把左边跟右边 这个东西算出来以后，把右边移到左边的，就可以得到 nj 是多少。好，这个东西呢，就把它写出来啊，算出来啦。epsilon j 的话，在室温下，那我们可以带我们正常自己都知道的公式，3/2 kT，然后算出来是这样的值。结果相除以后开个根号，然后你就可以得到2.7乘10⁹次方，非常非常大的数值。那这个数值呢，到时候会帮助我们去计算下面一页的东西。OK， 好，够吧？这样子大家就可以不用看我的 interface 那边选来选去，然后放大缩小，这是找到一个好方法的。Okay, so next one, density of the quantum states. All right. So we just said, okay, the nj is a really, really big number. So which means that they have many, many possibility, and all the number are closely packed. Closely packed. So this allow us to calculate that by using a really simple method like the counting the volume. Okay, so this is how I want to share with you here. Okay, epsilon, no problem, right? The n2 here. N2 is the vector sum, right? Mx squared, my squared, mz squared. So it actually looks really similar to this one's really similar to r squared, radius squared. So it looks like a ball, right? It doesn't look like a ball, look like a sphere. So when you try to find how many mx, my, nz, actually you are talking about a ball, okay? And also nx, ny, mz are all positive, so you only have positive octant, okay? So you just imagine that the sphere, only 1/8 of sphere need to be considered. So this region, okay, this region, and you can imagine that how many points in this volume, how many points within this yellow volume, indicating how many quantum number inside. Okay, what does that mean? Let's take a look. Ooh, sorry. Let's take a look. Let's take a look. Okay, so the number of states obtained within that octant, just this one, okay, the yellow region, actually is oh, this is really important, and I think this is really smart, really clever. Is the volume of the too big. The volume of the yellow regions. So what does that mean? Which means that because quantum numbers are all integer, right? So, and also they are all closely packed. So if you can imagine that, I need to plot something here. Okay, so I want to plot. Okay. Okay, it's not that perfect, but I need to move them in the proper place. Okay, so let's take a look. So imagine that you have a quantum number available in this point. 1, 2, 3, 4. So there are 4 quantum number available. You can imagine that. So imagine that how many quantum numbers here? 4, right? So actually, because every numbers are separated by 1, so which means that actually all you need to do is calculating the volume of this shape, and then you can get how many number of the quantum number, right? How many quantum number in this area. So if you want to know how many quantum number in this region, you just calculate the volume. I guess this is really genius. So here is the because there's only positive octane. Positive octane. So you only need to calculate 1/8 and 4/3 pi r cubic. This is the volume of the sphere. So you can get this ugly form. Okay, so the number of states contained in this particle in this sphere. So as you can see, next we are going to talk about degeneracy. G. Degeneracy is that when you specify certain level of the energy, right? So you specify this energy. So when the shell of the sphere crunk across the point, which means that that point is suitable for that energy. Okay, so when we talk about G for specific epsilon, which means that we are talking about how many numbers available in that shell. Okay, so here G epsilon D epsilon is the slightly thin shell, and then how many points inside that shell. So this is a N epsilon plus D epsilon. Of course, this is the outer surface, and the M epsilon is inner surface. When they minus together, you can have the volume minus volume, so you can get the volume with the little thin film, which means the degeneracy available in that energy level. Okay, so a little bit complicated, but I guess I try my best to let you to share with you. So the first one I mark with the wiggle sign, and N epsilon with the double cross sign, and we have equal to so we can use Taylor series, right? Taylor series to decompose this. So the N epsilon minus the epsilon times the epsilon plus blah 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 blah, and because the Taylor series, right? So I will name it single wiggle, and of course the remaining part, I will say they are all close to 0 because they are higher order term. Okay, so here I just trying to say FA plus H is the wiggle part. Okay. 哦，所以它还是会动哦。它还是会移动。我以为它就是整个都是维持在那里不动。Okay, and then FA is the double lines part, and F prime AH is the wiggle part only. Yes. So of course the rest of them they are all to the 0. All right. Okay. So after we done the approximation, we can do the differentiation for n and make it like this. All right. Times the epsilon. Oh, sorry. Times the epsilon. So here, g epsilon the epsilon can be looks like this. All right. So that's how we got how to estimate the degeneracy for each energy level. When you specify epsilon, specify energy level, you can get the corresponding degeneracy. And maybe you notice that there's a small room before the value, the equations. Okay, here, actually, we have a gamma s. What is gamma s? This is related to spin. So when you have a different wave number for each energy level, but actually there are still have some alternative choice for specific material. For example, if the material has spin, which is the quantum, magnet. Okay. So for example, if there's a particle, it's a boson or fermion, they can have the spin. Some of the particle, it can rotate only one round at a time. But some particle, they can have half rotation. So it have two choices compared to the first one. Okay, so gamma s equal to 1 for spin 0 boson, and gamma s equal to 2 for spin 1/2 fermions. So depending on the particle, it is. If it is boson, the gamma s equal to 1 because they only spin once around, so you can't see the difference. But gamma s equal to 2 for the fermion, because sometimes they can choose to spin down, spin up. So yes, so you have more choices here, more degeneracy here. Okay, so that's it. 好，那接下来我要解释一下，就是刚刚不是说 quantum number 是很多的，那表示说它的数量是密集的，而且是连续，也不是连续啊，哈，数字是1、2、3、4、5、6、7这样的 packed 这样上去的。那这样子的话，我们就可以去计算出它的n 是多少。那要怎么做呢？我们看 n2 的平方，这样它等于是一个 vector sum。你不觉得这个 n2 很像是一个半径吗？半径的平方跟那个球的感觉是很像的。那就好像是球里面的任何的坐标一样哈 ，nx、ny、nz 就好像球里面的坐标，所以我们就直接拿这个来看，而且它的 n 呢，它是正的，所以说它只需要考虑到1/8的球就好，原因是因为它只有正向，好正向，x、y、z 都是正的。那这时候要想一下，就是这个球里面到底有几个quantum number 呢 ？quantum states available 是可以让你选的。那这边就还蛮有趣的，就是说，其实因为它都是整体整数嘛，哈，1、2、3、4这样，所以你要算它里面有几个点，实际上就是算这个东西里面的几个体积，就像刚刚这边一样，我们这边有1个点、2个点、3个点、4个点，4个 quantum number 可以让你选。但是你可以看到，它们之间都是间隔是111。那实际上我只要算这边有4个体积是4的话，那边就有4个 quantum number 是可以使用的。所以说你要知道这里面 有多少个 quantum number，你就算它的体积就好了。所以1/8的球体积得到这样子的一个丑丑的数字 n epsilon。好，那这时候我们就要看看这个 n， 就是你只要给定一个 energy 就可以得到它的 n 可以是多少。那我们就想要知道 degeneracy 是多少咯。好，那 degeneracy 什么意思呢？就是在某一个某一个能量指定的能阶下，它有几种选择。那也就是说，在这个能阶下，它这个球面划过几个点，就比如说它可以选择多少个 quantum number 嘛，哈，那就是它有几种选择。那这时候这个薄薄的球面，那就是外壳 n epsilon 加 d epsilon 减掉内壳 n epsilon，然后应该说不好意思，应该不是外壳，哦，这个东西是球的1/8的球的体积，然后内缩一点点的球的体积，相减以后就变成壳，哦，相减以后就变成壳。那壳里面的这些点，就是我们可以选择的 degeneracy。OK， 所以就这样，这个东西减这个东西，哇，那这样看起来很难啊。不过没有关系，我们 Taylor series，所以我们就把这个对应成这个，这个对应成这个，然后后面这个东西当然就是它咯。然后后面这个点点点的部分就是高次项，所以就不要理它啦。然后算出来以后，我们就可以得到 G epsilon d epsilon 等于这个东西。那前面有一个 gamma s 是什么呢？因为 quantum particle 它可能会有spin， 这个 spin 就是 quantum magnet， 就是有些材料，就例如说像 boson 的话，它就是每次都转一圈，它就只有一种状况了哈。但是有fermion 的话，它的 spin 它是可以往上转，也可以往下转的，转一半。好，那这样表示说它有2种选择。就如果今天是 fermion 的话，这边的 gamma 就是 s， gamma s 就是2。哦，然后如果今天 boson 的话，这边就是1，就当做是没有，等于是这个 gamma s 就是一个校正就对了。Okay, so we talk about the boson and fermion, but actually, this is many types of elements, particles. So you can have fermion and boson, and you can see electron is part of fermion, and photon is a part of boson. Okay, so just a type of our nature. OK， 好，总之就是自然界有这样子的现象，它有很多种不同的颗粒。然后电子的话就是 fermion， 然后光子的话就是 boson。好，就这样。OK，so I don't know if I have the video。我要怎么看离线？Yes。OK，let's take a look。I quite like this video. Explain what is the spin quantum magnet. We don't need to say anything. You can understand. That's really nice. Two choices. Yeah, two choices. 而且还有音乐，很好听。OK。Harris, yeah, really nice. Made by friend. Good. Yeah, so maybe it can help you to have some idea about the spin. Okay, and I guess it's a time for 20 minutes break. So I will see you later. All right, thank you. if there's any difficulty to see my slides or my presentation, just let me know. Thank you. 哦，看起来 Good Note 比较好。好，请问线上可以听得到我的声音跟看到我的荧幕吗
看得到，
？Hello，
看得到。
谢谢，感谢。好，那我们就要开始啦。喂，嗨，我很高兴我终于找到一个很好的方法，就是可以把我的东西投影到荧幕上，然后可以让线上的同学看得到这样。这个东西叫做 AirPlay。大家好像觉得 AirPlay 不是很久以前就有了吗？哦，不一样。这个 AirPlay 以前我试过，就是如果今天我用这个 iPad 投影到这里的，就是教室里面的 AirPlay 的话，会很慢，就是我写的这个笔记会没办法投的很好。那最近不知道为什么它好像有新的功能，就是我可以直接投影到 MacBook 上，所以我刚刚就想要试图去投到 MacBook 上，但是刚刚一开始为什么10分钟就是 delay 10分钟，原因是因为我这台电脑不知道为什么不能上 WiFi，所以我就想说糟糕了，不能用 WiFi 了。以前我都是用 QuickTime 去直接去抓这个东西的这个 iPad 的影像讯号。那现在的话，那 iPad 影像讯号在 QuickTime 里面，它就是直接就是 mirror，就是你看得到我的 interface。但是现在如果是用 AirPlay 的话，我刚发现竟然连上这个就可以使用 AirPlay。我这边其实是没有网络的，我现在这个 iPad 其实是没有网络的，所以其实是用线 AirPlay 到里面去。对，然后呃，对，然后我觉得还蛮有趣的。那接下来就是差别在于，就是我如果今天用这条线连到就是把我的荧幕投到上面的话，我如果使用 AirPlay，我可以使用简报模式，这样就看不到我的就是 user interface。那后来我发现一件事情，就是这个是这叫什么notability。我现在这个是 notability，它的 presentation mode 我觉得有点怪怪的。就例如说我现在放大，我的放大在这边写的时候，如果我往下走。你看你的荧幕也往下走，可是问题是你根本不需要跟着我往下走啊，好奇怪哦。所以我不太喜欢这个。刚刚我又尝试了一下，我使用 Good Note，Good Note 的话就好像还不错哦。Good Note 的话，我在这边写字，但是我移到下面来的时候，你没有发现，你不会发现我移到下面来了。所以虽然我这边荧幕整个在移动，但是你这边都看不出来，所以这才是真正的简报模式吧，我觉得。而且它这边还可以，你还是可以放大，所以我觉得这真的是一个目前来看 Good Note 的 Presentation Mode 是我最喜欢的。好，大家可以看到我为了这件事情花费了很多心血，那我就蛮喜欢做这件事情的，因为我自己在呃我就很喜欢做就是那种如何用3C 产品，然后做到一些呃可以让我自己教学啊，或是更顺畅的事情。那我之前还就是有去其他学校去分享我的那个 setup 给其他的老师听，这样。那现在看来，我就得要换一下了，因为我找到更好的方法，我投影片要改了。对，我觉得对是一个很不错的分享，这样，而且这样子的写的字会比 Apple Pencil 好看，大家应该觉得吧？就是它那个钢笔的那个笔触 是有粗有细的。每次看我就觉得哇，真是开心。以前买了 Apple Pencil，我觉得很棒，是我的手可以放在那个 iPad 上，可是它的那个笔触就不会像这样子这么的像真实的笔在写一样。所以这个也不错，而且这个你看，这个是一个很特别的触控笔，它触控笔上面是有个板子的，有一个薄板，很奇怪吧？但是这真的蛮好写的，所以我花了很多钱买 App， 然后很多钱买笔，对，所以还有很多钱买大的 iPad， 对啊，所以就说每次来的时候都是一大堆 set up。当然我还有很多浪费的，例如说买了一个显示卡，就是那种影像截取卡，我想要截取我的 iPad 的那个影像，然后再投到任何地方去，但那个没有用，好，就白买了，好，所以我浪费很多钱。好，不过希望大家喜欢我的上课方式，OK。但是如果你有任何建议，都可以告诉我。I just want to share that their MacBook has a new update for the AirPlay, so it makes the AirPlay become more easier. So I just connect the cable and then I can do the presentation mode. And you can see better presentation. Yeah, so let's continue our lecture. I'm really happy about this. So after we talk about the spin, right? And then we can talk about the fermions and bosons. Okay, so as we can see, fermion has spin. You can have a positive half or minus half. So you can have half integer spin like this. And fermion has a really interesting phenomenon. It's called Pauli exclusion principle. Pauli exclusion principle. Okay, so which means that they are not good at get along with others. Okay, so they cannot share the same degeneracy. So cannot do that. All right, and the boson, the integer spin, they have integer spin, so 0, 1, 2, so you can't see any difference after they spin, and also they follow Bose-Einstein statistics. Their behavior follow Bose-Einstein statistics. Okay, and they can share the same degeneracy with others. So yeah, that's it. Just saying that fermion and boson has two different behavior and two different type of spin. OK， 好，基本上就是在讲我们接下来会看两种 particle， 第一种是费米子，第二种是波生子。然后费米子它就是会有一半的 spin， 然后所以它就是会有正1/2或负1/2的旋转。它会遵循着 Fermi Direct 的统计状况 ，OK， 就是它的行为啊，它可以用统计这个 Fermi Direct 的统计来解释它，然后它会有包利不相容原理，就是它不能分享同一个 degeneracy 跟别人，然后 boson 的话，它就是遵循 Bose-Einstein 的统计行为，那它可以跟别人分享同一个能阶 ，OK， 就这样。同一个 degeneracy. Okay, so next let's talk about let's just do example. Consider a gas consists of 1 kilomole of helium atoms at standard temperature and pressure (STP), and calculate the degeneracy G. Please calculate the degeneracy G epsilon for the energy level. Blah blah blah. Take gamma S equal to 1. What does that mean? Which means that we are talking about boson, right? Boson. Okay, so what is the approximate ratio of G epsilon to the number of atom? Okay, so let's continue. So N equal to 1 kilomole, right? 1 kilomole. And STP tell us V equal to 22.4 m cubic, and epsilon equal to 2/3 KT equal to 3/2 times 1.3 A times 10 to 23, okay, times 237, and equal to 5.65 times 10 to minus 21 joule. Okay, so you got N equal to 1,000 more, STP equal to is indicating volume is has 22.4 meter cube, and epsilon is 5.65 times 10 to 21 joule. And oh, right, I forgot to write down why we need to these number, because I guess you know, because J epsilon equal to gamma S 4 square cube 2 I V H cube and 3/2 epsilon 1/2. Yes, so that's why we need to calculate epsilon, epsilon, V, and yeah. Okay, so what we left, N and H, right? So let's continue. The N for the helium, 1 kilomole helium, M equal to 4 AM. You can check it, Google it on the internet. It's called AMU called atomic weight, dA, Dalton. Okay, and you can have 4 times, if we transferred into 1.661 times 10 to minus 22, 27. So you can have 6.644 times 10 to minus 27. Okay, so you can see here, don't forget the unit transfer, okay? Right, and one thing left is H. H is 6.626 times 10 to minus 34 joule second. Right, so now we are more or less ready. You can get A G epsilon equal to 1 times 4 square root I and times 22.4 6.626 times 10 to minus 34 cubic. Wow, it's long. 6.644 times 10 to minus 27, 3/2 times 5.65 times 10 to minus 21 to square root. 5.57 times 10 to 52. Wow, this is a really big number. Okay, so you can see that the G epsilon for the specified value will be so big. Okay, so big. Right. Hope you can see this clearly. Well, sorry, let me rearrange a bit. Okay, it make you feel, yes. Oh, I really like this handwriting. I really like that. Okay, so next one, you can have, the second one is the approximate ratio of G epsilon to the number of atoms. G epsilon to the ratio M. Okay, so 5.57 times 10 to 52, such big number. And 6.02 times 10 to 26, right? 1 kilomole. So 0.925 times 10 to 26. Okay, so that's it. 为什么刚刚有日本腔 ？OK， 哦，对了，讲到这个，就是日本的小男孩好可爱哦。就是我上一次我的小孩，我最近送我小孩去足球课，然后礼拜天的晚上，然后我就看到，就是他有一个同学，就是日本小男孩，超可爱的。他就是会 TT 就会跟他爸爸说，看我看我，然后看我很厉害吧，然后这样，然后就会跟他爸没事讲一下中文，没事讲一下日文，超可爱的。对，不知道为什么，就小孩讲不同的语言就觉得超可爱。Okay, I just talk about. I found that it's really cute if a kid speaking foreign language. So cute. I don't know, because I don't understand what he or she talking about. But it's really cute. I don't know why I brought this up, but right. So I've done the examples. Hope you can help you to understand these calculation better. 好，讲中文就是我们要算它的 G 是多少，那它是 helium 在1K mol 下面，然后是标准的温度跟压力，然后在能量是 epsilon 等于3/2 kT 的状态下，然后它伽马 S 等于1的话就是 boson 嘛哈。好，那我们就算一算啊哈。那这是我们的公式，所以说我们必须要把里面的东西都算出来。N 要算出来 ，STP 的 V 要算出来22.4，我们之前都算过了。Epsilon 的话就可以算出这个，然后 M 的话呢，1 helium 嘛，1 kilomole 的 helium 就是4 AU，然后乘上这个值，然后小心这个 AMU 它其实就是 delta 然后它是1除以1000 NaKg 哦，所以它这个要自己要叫什么？单位换算要注意一下，好，这边要小心。得到 M 等于是这样多少以后 H 又是写出来 ，OK 没有问题，算出来以后得到52次方这么大的数字。那第二小题它就是说，它的 ratio G epsilon 跟 N 的比例是多少？哦，它就这样算，然后得到一个很大很大的数字。这告诉我们什么意思啊？就是它有很多选择啦，一颗 particle 有10的26次方这么多选择，超多选择的意思。OK， oh, so I forgot to tell you the meaning of the second one. Why the problem asks us the ratio between G and N, which means that for each particle, it has 10 to 26 choices. So which means that the choices are abundant, so many for one particles. Okay, so which means that G is really, really big compared to N. Okay, so this is some assumption we may use later. Okay, especially for the ideal gas. Okay, that's it. So we done the PDF 5. Let's move on to PDF 6. PDF 6 is classical and quantum statistics. Okay, so I believe the sixth one is really useful, or really important, I would say. It tells us how to determine the statistic. What is the statistic? So we can have a look. First one, we are going to see the Boltzmann statistic. Because the difference between particles, difference of particle, they have different behavior, so they will resulting in different statistics. Okay, so as you can see, different material may have different statistic we need to apply. So for example, useful for solid and liquid. Okay, the solid liquid means that the particle is distinguishable. Okay, and non-interacting particles. So especially, so later, if you meet material like solid or liquid, just use Boltzmann statistic. All right, so let's do it. So of course, we need to find the statistics. We need to find the formulation for this statistic. So we need to find the constraint as well. The constraint, conservation of particle. J equal to 1, and J equal to N. Like that. Conservation of energy, of course, J equal to 1, and J epsilon J equal to U. Okay, so these two things, I believe you know that. Our goal is find, this is really important, find the occupation number. What is occupation number? Which is NJ. So what is NJ? The value of NJ for each energy level J when the thermodynamic probability is a maximum. Okay, so you can see that you have N1, N2, N3, N4 until Nn. Okay, you have many N here. And what's the set of all the N which make that state has the maximum possibility to present in the world? That's what we are going to seek, determine. Okay, so the NJ, of course, will determine the probability. So we need to see what is the N looks like. N1, N2, N3, N4 look like. Okay, this is a little bit complicated, but our goal is that we want to find the distribution of N to make the probability of that system has the maximum probability. Okay, so before we talk about the maximum, we need to listed all the possibility, right? So how many ways to choose N1 particle from N and put that in the energy level 1? So Cn get N1, right? So N factorial over N1 factorial, N minus N1 factorial. Okay, I know you know that, no problem. This is okay. And then there are G1 degeneracies in energy level 1. So how many possibilities? Let's take a look. Let's take a look. So we have degeneracy like this, such many degeneracy. And this is degeneracy. And how many possibility? How many possibility? All the M1 in the energy level 1 can all put into all put into here, or here, or here, here, here. So there are so many possibilities. Well, this is the first degeneracy. First degeneracy 2, 3, 4, and G1. There are G1 degeneracy, and each degeneracy can be put in the in the G1 or G2 and G3. So you have really big G1 N1. How many possibility? G1 to N1. So in total, how many ways to put N1 particle into level 1? N factorial G1 N1 divided by N1 factorial N minus N1 factorial. So that's how many ways to put N1 particle into level 1. This is yeah, that's it. 好，我们要解释的就是说，第6章很重要的原因是因为我们要计算算出很多种 statistic， 就是统计。什么是统计？就是我们用一个数学方式去表示一种系统的行为，是什么样的行为？它是照着这个它的行为会造成什么样的统计现象就对了。那有很多不同种，就是根据 particle 本身它自己的现象，就会有采取不同的统计学。那这边我们使用 solid 跟 liquid 的话，表示说它们是分得开来的，因为它们位置会固定，它们有固定的结构嘛，所以它们就是被分得开来的，然后它们没有互相作用这样。那我们要解释这件事情，它们叫做 Boltzmann statistic， 也就是说以后 solid liquid 的话，就是使用 Boltzmann statistic。但是要算这个东西，一定要先用解的方程式的方式嘛，所以要写一些constraint 就是 particle 的数量要固定，能量也要固定，这没有问题。那接下来这个超重要的，这个 goal 超重要的，它是说我们必须要去找到 occupation number， 也就是我们的 NJ。我们有 N1、N2、N3、N4 这些数字嘛，对不对？这些数字可以是 N1 可以是1，可以是2，可以是3。每一个 J 每一个 level 都可以有不同的 particle 的数量，但是哪一种数量的分布会造成这个系统有最大的几率出现呢？这就是我们想要知道的。那所以我们就开始看要写最大的几率之前要先列出来。那我们就 CN 取 N1， 然后取到第一个 level。我们先考虑第一个 level。先从 n 个 particle 里面取出 n1 个来放进去 level 1， 那有几个方法？那当然就是先成这样。但是呢 energy level 1还有 G1 个 degeneracy 还有不同种方法所以我们要把 n1 放到 G1 个 degeneracy， 有几种方法呢？因为 n1 是 N 是 distinguishable， 对不对所以说它可以放在第一个，全部都放在第一个也可以，放在第二个也可以，放在第三个也可以，都可以。好，那就有 G1 N1 次方，那把这两个相乘起来，你就可以得到这个总共就是 N1 放在 energy level 1里面有这么多种方法 ，OK？ But now we'll only talk about level 1. How about level 2? Level 2 is okay. Because now your n is minus n1. You only have n minus n1 left, right? So your total number, for the level 2, the total number available atom is n minus n1. Okay, so G2, of course, you have the same formulation and you pick up n2 factorial. So level 2 looks like this. I guess you have no problem about that. And thermodynamic probability, which means that all the possible way. So you need to level 1 times level 2 times level 3 times level 4, blah, 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 blah. So you can get this one. So WB, the B stand for Boltzmann statistic. Okay, so N1, N2 to Nn. You need to multiply all over. Okay, then interesting happened. You can imagine that n minus n1 factorial divided by, you can cancel each other and then cancel for the next one and so on, so forth. So everything becomes simpler, become n factorial and g1, n1, g2, n2, g3, n3, blah, 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 and n1, n2 factorial, n1, n2 factorial, n3 factorial. Okay, blah, 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 blah. So looks a little bit easier now, but don't worry, I will make it even more simpler. It's called n factorial multiple multiplication, nj factorial g j n j. Okay, so that's called WB thermodynamic. Sorry, Boltzmann statistic thermodynamic probability. It's called Boltzmann statistics. Okay. Now, this is all the possibility. Oh, sorry, all the permutation, all the thermodynamic probability. How many ways rather than true probability? Okay. Then we shouldn't forget our goal. We need to maximize. What is maximize? Maximize it. Okay. We want to maximize it. We need to maximize the WB to find this. We need to find the solution. We need to find the solution of N1, N2, N3 to Nn to maximize WB to make this the greatest possibility. So this is our goal. Don't forget this. 好，那我们刚刚讲的第一个 energy level 嘛，哈，那我们讲到第二个 energy level 也很简单，就一样画葫芦，只是现在的 n 呢变成 n 减 n1 了，因为你先把 n1 拿走了嘛，哈，所以后面几乎都一样。那我们就把它所有的可能性都要乘起来哦 ，level 1、level 2、level 3都要乘起来，乘起来以后发现它可以消成变成这样漂漂亮亮的，把它写成这样子的式子，它叫做 Boltzmann statistic。波兹曼统计，但是这个问题是我们现在重点不在这里，我们这只是一个过程，我们的真正的目的是要找到 N1、N2、Nn 这些值要长什么样子，会让 WB 最大，就这样，好，这是我们想要做到的事情。Next, if we want to find the maximize W, we need to use some math tool called Lagrange multipliers. Okay, there's plenty of definition of steps. We don't need to do. I won't explain this here. We just directly use that. Okay, and then you will understand. 就是我们要用拉格，算了，你自己知道，反正就是乘的东西，然后它就可以帮助我们去算 WB 的最大值。Okay, so what can we do for this? Okay, our goal is find a set of x1, x2, xn to maximize the function of x1, x2, xn. Okay, this is our goal, no problem, right? And we also subject to some constraint. Of course, I guess you understand what does that mean? The x is actually the mj, right? So you can see it can be written as two equations, this constraint. Epsilon j is constant, of course. Now, what is Lagrange multiplier? Lagrange multiplier is that we want to find the function maxima set of x1, x2, n to maximize the f. We firstly define a new function, which will including the phi n the constraint. Okay, so the new function, I guess is gamma. Okay, gamma x1 x2 and is actually the original function. Original function and adding constraint equations. Okay, so the new function is original function plus constraint function, a constraint equation, but with alpha and beta. The alpha and beta called Lagrange multipliers. Okay, you just multiply two coefficients, alpha and beta. And of course, phi and I don't know how to say that. Phi and psi, maybe. Okay, I don't know. Okay, so your unknown will be, if you want to solve this equation, the unknown must be unknown n plus 2. Of course, n is what you expected, right? The x1, x2, xn, and 2 is alpha and beta, right? Okay. So now we're going to do what we are going to do. Find a maxima. We want to, for a maxima, the df equal to 0, right? If you have x1, x2, xn, you must make the df equal to 0 because that's what you want, right? x1, x2, xn to mix the f maxima. So df equal to 0. And because the set of x need to satisfy the constraint as well. So phi equal to constant, because they are constant. You do the differentiation, it will become 0. No problem. And the same for the second constraint equation. So this tells us if we do x1, x2, xn, do the differentiation separately, the new function will equal to 0. And to the all the x1, x2, xn, if you do the differentiation for them, they are n equation for you to solve. And if you do the partial for alpha, you can get phi, no problem. And also do the partial differentiation beta, you can get phi, really, psi, anyway. So you can see there are equation n plus 2. There are n plus 2 equations. So n plus 2 equation and n plus 2 unknowns. So now you can solve all of them. So that's the idea of the Lagrange multiplier. We just borrow the behavior of differentiation of function equal to 0, give us maximum. Okay, and also the constraint, they need to be constant. And then we can do the differentiation, they become 0 as well. So that's the thing we want to, we kind of using this trick help us determine the n1, n2, n3, and x1, x2, x3, xn. So if you can understand this is Lagrange multiplier. 好，那我们现在来讲是这个 Lagrange multiplier 怎么做的呢？我们的目标是要找到 x1, x2, xn 最大化 f 这个函式。那别忘了我们还有几个，在最大化的同时，还是要有叫什么 限制哦，要符合这些限制。方法就在于这个 table 就在于你要先做一个新的函式，它包含原本的函式，再加上你的第一个这个限制函式乘上一个 alpha， 第二个限制函式乘上一个 beta， 这个 alpha 跟 beta 就叫做 Lagrange multipliers。OK， 那不要忘了，就是他们这边都这个 phi 啊，那个 psi 啊都是0，好，不是0，都是常数，都是一个常数。那如果今天这样写上这个了以后，我们就可以利用一个现象，就是说这个解啊，这个 x1 x2 跟这个解，我们要解它，就是要找出它能让它最大这个 original 的 function 最大值嘛，所以我们就做它微分等于0，这个应该没有问题。但同时他们也要满足这两个式子啊，满足这两个式带进去以后，他们会得到一个常数，这个常数一微分，它也会等于0，所以你会发现这边虽然有 n 个未知数，阿尔法跟贝塔 ，n 加2个未知数，但是你做一个微分，你每一个都可以去做微分哦，你做微分，阿尔法也是，贝塔也是，都可以做个微分，都会给你等于0啊。那就是它这个新的函数都会给你0这个值，所以你就会得到这么多组 equation，n 加2个 equation，n 加2个 unknown 就可以解出来了。好，这就是我们的它的概念。Okay, so next, the Boltzmann distribution, we need to apply the Lagrange multiplier for Boltzmann distribution. We want to maximize W, and W looks like this, right? Okay, we want to maximize to find the N1, N2, and Nn to get this. But this is too difficult, right? They are multiple multiplication. It's really difficult. So how about we change our goal? We don't want to maximize this. We make it simpler. Can we maximize natural log W B instead? Can we do that? Well, sorry, I shouldn't add in B because I don't have B here. So just saying that if you want to maximize this, we do the natural log W. We maximize natural log W. Can we get exactly the same set of N1, N2, Nn, which maximize the natural log W? Natural log W. Yes, we could because natural log W, natural log X and Y, actually they are 1-to-1 mapping value. As you can see, and also it is proportional. As you can see here, all the value here are 1-to-1. So if you have X equal to 4, you have one value here. If you have a value of 5, you have one value here. So natural log W and W, they are one value correlated. Each value, they are all correlated. And then if you have greater W, you will have greater natural log W. So basically, if you maximize natural log W, you simultaneously maximize W as well. So to make this multiple multiplication easier, I changed our goal to maximize natural log W. It is because it is maximized for the same set of N1, N2, Nn for W. Okay, so that's the first trick. And then we just do exactly the same thing here. Okay, the natural log W is original function now, and the phi and psi equal to 0. So we do exactly the same thing. Okay, so how can we do that? I will do it in the next page. 好，我们要讲的就是这个波兹曼常数波兹曼分布要把它求出来。这个分布就是所谓的 N1, N2, Nn 到底怎么分布嘛？那我们发现这个东西是连乘实在太难了，我们要最大化这个东西太难了。那数学家就想到一个方法， 连乘的话，把它变成连加比较简单，就做 natural log w。但是你可能会想，哎，我要最大化这个，我不是要最大化 natural log w，可以吗？其实可以的。我们来把这张图看一看 ，natural log w 跟你的 x 轴的值其实是完全一一对应的。你的 x 是多少，你就可以得到一个 natural log w 值是多少。这样就是它是一一对应的值，这没有问题。而且你的 x 越大，你的 natural log 值就越大。所以其实你最大化 natural log w 的时候，你的 w 也最大化啦，而且它的值是 n1 n2 是固定的，你可以用同一组的 n1 n2 得到最大的 natural log w 跟最大的 w 值同时。好，所以呢，我们把它做的很简单，就把它 natural log w 以后，然后这边就变成我们的 original function， 然后就做一模一样的事情。要怎么解呢？下一个页就可以解给你看啦。So natural log w here equal to natural log n factorial and wow, blah, 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 minus blah, blah, blah. Okay, this is a little bit ugly, but don't worry, we have Stirling's approximation. Okay, Stirling approximation to make the ni factorial become natural log ni plus ni. Okay, so after applying a Stirling approximation, you can get these. Then here, this is ugly, but don't worry, it will disappear later. Don't worry. And yeah, so we just do the differentiation for nj. Okay, right here, n factorial is a constant. So if you do the factorial, this one vanished, 0. Okay, so you won't see anything here, nothing. All right, so the second one, okay, second one is a bit, you need to, yeah, we just do this. Okay, then we don't need to care about this because this is a constant, so we just neglect it. Okay, so now we only focus on the left three, the remaining 3 terms. And also, don't forget the Lagrange multiplier part plus alpha mj sigma n I plus beta nj sigma a sigma I n I epsilon I equal to 0. Okay, so this is next one. Next step is a little bit important. Okay, here when doing differentiation for nj, the term is non-zero only when I equal to j. Wow, this is really important. As you can see, wow, this is summation. You want to do differentiation, you need to dealing with a lot of terms, but actually not. Okay, don't be frightened by these sigma term, because if you do when I is not equal to j, they are different variables. So when you do the partial differentiation, it will gone, right? It becomes 0. So the only thing left when you do the differentiation for summation is I equal to j. So all you need to do is just do the nj, differentiate nj natural log gj. So you got natural log gj for the first term. Okay, it's easier, much easier. For the second term, it becomes natural log nj minus nj over mj. Again, the only I equal to j term need to be considered. Then again here become 1, no problem. And you do the differentiation for the later, you got alpha plus beta epsilon j equal to 0. And then mj over nj cancel each other. So you got natural log nj over gj equal to alpha plus beta epsilon j. So nj over gj equal to exponential alpha plus beta epsilon j. Okay, so this is defined as epsilon fj of epsilon j. Okay, so basically this is the distribution maximize the function. Okay, maximize of the WB. So the question is that what is alpha and beta? Don't worry, I will do it later. I will explain later. But the thing is that when the distribution of the particles satisfy with nj over gj, the degeneracy in nj, okay? nj and dgj equal, the ratio of that follow equal to this one, it will make the WB maximize. So yeah, that's it. We finally obtain the N1, N2, N3, N4 looks like. What's the distribution of them? We determine that they need to satisfy this ratio, NJ over GJ ratio. OK， 好，那我们把刚刚那个 Lagrange multiplier 已经写完了哈。那 natural log W 呢就写成这样子，然后这边有 factorial， 我们就用 Stirling 把它分成两项。然后呢，第一项。我们接下来当然就是要做微分嘛。那这边你会发现这一项不见了，原因是因为这个 n factorial 它是整数，它是常数。那你对 nj 做微分，它早就不见啦，所以根本不用管它啊，这边就不用写了。好，然后第二项再写在这里，第三项写在这里，第四项不对，2、3、4项就写在这里。OK， 好，然后别忘了我们还有那个 Lagrange multiplier 的项，对不对哈？就把它写出来。好，然后呢？接下来这个好，那接下来我们就做微分。这边微分有个问题就是，哇，这边 summation 很可怕，我们要算很多个项哎，怎么办？不用担心，因为我们的 nj 啊，它做偏微分。如果今天 I 跟 j 不等于的话，如果今天是 n1 项要做 n2 的偏微分，那当然就等于0啊，对不对哈？所以只有 j 跟 I 是同样的值的时候，那个项才必须要我们算出来，其他都是0。所以啊，你根本不用看这个啊，你只要把 I 变成 j 就好，然后做微分，你就可以得到 natural log j 第一项。这个的话就是第二项，这个的话就是1，因为它只有 I 等于 j 是一样的嘛哈，是可以被微分的，然后就1。后面的话就是 alpha 加 beta epsilon j。好，那我们就发现这个可以砍掉，然后做一做就可以得到这样子的式子。那这告诉我们一件事情，就是如果今天 n1、n2 这个东西啊，它跟 GJ 的比例是符合这个式子的话，它就可以让这个材料的可能性是最高的。OK， 好，那这蛮酷的，就这样。Okay, I guess you need to have a break for 10 minutes. Sorry, I make this. I delayed 1 minute. I will give you back 1 minute. So see you after 10 minutes. Thank you. See you later. 好，请问线上的同学有听到我的声音跟看到我的画面吗？
可以。
谢谢，谢谢。Okay, so let's continue our lecture. Final hour. 加油，加油，加油。Okay, so we just determine the ratio between MJ and GJ. It needs to follow. It needs to be equal to exponential alpha plus beta epsilon J. If they follow this equation, it will maximize WB. Okay. So what is the WB? Lagrange multiplier beta. It will be natural log GJ minus blah 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 equal to 0. This is okay. But you can imagine that this is epsilon J. This is epsilon J. So you can times MJ and then do the summation, and you can compare with the constraint you have. So suppose you times MJ and summation, you can get these. Okay, and then you can to the right make the alpha m and beta u to the right hand side. Okay, so this equation after times mj do the summation j, it looks like this. And then you can compare to the natural log w. The gray dashed range means that we have discussed in the previous few pages. Okay, so this we have done that before, and we can compare this part and that part. They look really similar, right? They look really similar. So we can substitute this natural log w equal to natural log n factorial plus m minus alpha m minus beta u. And of course, these are constant because m is the total number of the particle, right? So n natural log n factorial plus n minus alpha m, they're all constant. So you can say this is a constant c here. So natural log w equal to c minus bu. And for the statistical thermodynamics, you have S equal to K natural log W. So we just substitute this here. And you can have KC minus K beta U. Of course, KC is the constant as well. OK。以为我刚刚 Siri 问我说有什么可以帮我的，我猜我刚刚讲的那个 C 可能他觉得我在叫他吧。应该没问题吧？好，就这样。Okay, so next, S no is the constant, and K beta U. All right, so S equal to this, and if we do the partial differentiation for U at constant V, you can have this one equal to minus K beta. No problem. This is easy. Okay, just straightforward from left to right. No problem. But for the classical thermodynamics, we still need to, we can connect statistical thermodynamics with classical one. Okay, you can see ds equal to du over t plus pdv over t, no problem. And you can do this as a differentiation. Then it's nice. You can compare. You can compare here. You can write down to make the ds has two contributions, du and dv, and this is the slope, right? So by comparing this du part, you can say partial s over partial u at constant v is 1 over t. You can see that. So connect these two, you can have beta equal to -1 over kt. Okay, so that's how we can get the beta. All right， 好，我们要算 beta 哈 ，Lagrange multivariate 的 beta。那这个东西前面我们已经算过了嘛哈，那只是我们发现哦，这边有个 epsilon j 耶，那我们可以跟它来比较一下，我们乘上 nj 以后，全部乘上 nj，然后全部 summation 起来，来比较一下，应该说把这个东西可以带入进去了哈，所以说这边就变成 u 了，然后我们就把这个东西这两个东西拿到右边去，得到这个式子。那怎么解呢？我们发现 natural log w 呢，以前我们解过了，好，在前几页有解过了。我们发现这一个两项跟这两项几乎长得一模一样啊。那所以说我们就直接把这个东西替代成负阿尔法 n 减贝塔 u， 就可以写出这样子的一个式子。那不要忘了这边都是 constant， 因为 n 就是 total number 嘛哈，然后它是 constant， 所以我们就把它写成 c 减贝塔 u。那接下来呢，我们就可以连接一下，我们需要靠两个理论帮忙，一个是 statistical， 一个是传统的。好，那 S 等于 K natural log W 可以就写出来，就可以得到beta 呢，如果你对 S 做能量的微分，你就可以得到这个式子。好，接下来我们就卡住了，没关系，我们还有 classical one。classical 的 ds 怎么写呢？它可以把它写成这样子以后。然后我们也会发现，如果我们看 ds 是两个共线 du 跟 dv 的共线的话，它这个前面的斜率就分别会等于 e 除以 t 跟 p 除以 t 嘛哈。那没关系，我们就只要看前面这个就好。partial s over partial u at constant v 会等于1分之 t， t 分之1。好，写出来以后，这两个相等。也代表这两个相等，所以贝塔就可以算出来啦。好，非常的聪明。OK， 接下来是 接下来是 Lagrange multiplier alpha. So now let's talk about alpha. The alpha, yeah, you can see that we just use the second constraint, right? Now we use the first constraint. So this is the result we get, and we can make the GJ to the right hand side, and we just summarize, do the summation, just summation J, and we can compare with nj equal to n, right? So the n here equal to blah, 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 no problem. And exponential alpha can be done by make this right hand side to the left hand side. So you can get exponential alpha equal to such ugly things. Okay, but don't worry, it will look a bit better if we can make it write it down here. Okay, so this is fj equal to nj over gj, which is equal to exponential alpha plus beta epsilon j, which is equal to n exponential epsilon j over kt dimension nj equal to 1 gj exponential minus epsilon j over kt. Okay, so that's the final form of fj. And if you can see that this one is actually the sum over states. It's sum over states. So we can say this is partition function z here. Okay. So now we really done the calculation for the Boltzmann statistics and the distribution. Okay. And then this is really it's really interesting to examine this function. You can see mj are determined by t and V. T and V. V, where is V? V is actually related to epsilon J. Remember, the epsilon J is proportional to volume minus 2/3, right? So NJ is determined by epsilon J and K, T, so which means that NJ determined by temperature and volume. So here, T and V determine N1, N2, and Nm. In classical theory, temperature and volume also define a thermodynamic state, right? So we have really good agreement between statistical and classical thermodynamics. Okay, that's good. 好，那我们算阿法嘛，阿法比较简单了哈，阿法就把这个答案拿过来以后，把 GJ 拿到右边去，我们就有 NJ 等于这个东西。那很简单，我们直接做 summation 就可以，它等于 N 了，然后就可以得到这个式子。那我们要阿法嘛，所以把这右边这个东西整个拿到左边去以后，得到 exponential 阿法等于这个东西，好丑，不过没关系，反正我们就把它带进去咯。我们的 FJ 呢就会等于这样子丑丑的东西。那我们可以看到下面。其实不就是我们的 sum over state， 就是加所有的状态的加总。你看所有状态的加总，而且还要乘上它的 GJ， 那不是它的 partition function z 吗？所以下面就是 z 啦。那这边就是我们的 FJ 的结果。那这边可以讲一下物理的状况和物理的意义。我们看到这个 NJ 啊它的值它必须要去满足这个 Boltzmann distribution 嘛，对不对它的比例。那这比例是怎么决定呢？温度跟 epsilon J 来决定的，对不对那温度这没有问题，那怎么会跟体积有关？别忘了我们的 epsilon J 是跟我们的体积是相关的哦。还记得我们在前面的时候有用绿色的东西来画，绿色的荧光笔画嘛，对不对绿色荧光笔，我们用绿色荧光笔画这两个东西，对不对那所以说就是我们讲过了那我们的 epsilon J 就跟 V 有关，所以 T 跟 V 会决定 NJ 它的状态。那跟我们的传统热力学一样 T 跟 V 的确也会决定一个状态，所以是完全相符合的。Okay, next, let's give this example. They are consider a system of undistinguishable particles, which means that Boltzmann statistic, right? At temperature T, okay, and while with available energy levels epsilon 1 and epsilon 2, and epsilon 2 is greater than 1. Only 2 available energy levels. So of course, this is a toy model. This is fake. This is just toy, not a real state. In the real world, we have epsilon 1, 2, 3, 4, 5, 6, 7, and until really, really big number. Okay, so this is only toy model for you to practice. Okay, and A determine the equilibrium values of the occupation number N1, N2, and the energy U of the system as a function of temperature. And here we also say G1 equal to G2. All right, so let's take a look. What does it look like? So determine the equilibrium values. And I equal to N G I exponential minus epsilon J divide by KT and Z. All right. So M1 equal to, okay, here, G1 exponential minus epsilon 1 KT divide by G1 exponential minus epsilon 1 KT plus G2 exponential minus epsilon 2 KT. Okay, and you can imagine that you can see that G1, G2, they are the same, so they can cancel each other. But this is M1. Oh, by the way, you can see the Z here. Why only we have two terms? Because we just said only two available energy level. Okay, so Z is sum over state. So you only have two level. So you just add two. So Z equal to two terms. Okay, so later this is N1. How about N2? N2 equal to N. Oh, sorry, I forgot N here. Okay, N exponential minus epsilon 2 kt exponential minus epsilon 1 kt plus exponential minus epsilon 2 kt. So this is N2 looks like. And yeah, I need to emphasize this. This is sum over states. Okay. Then we are more or less ready for the question problem 1. Determine the equilibrium value of the occupation number N1, N2. Yes, we have done that. And the energy U, okay, of the system. U, of course, is summation epsilon I M I. So all you need to do is N exponential minus epsilon kt plus exponential minus epsilon 2 kt. And then, oh, okay, 懒得写了 copy 组织贴上 okay, but we need to times epsilon 1 and epsilon 2. Okay, so this is U here. Hope you can see it a bit. Okay. Then, next, show that the specific heat is given by CV equal to this. Okay, and they use delta. Okay, so if we use delta, we can also apply to the first one. All right, so it's not a big deal, but just make it looks better. Ding. KT. When you use delta, it looks a bit better. Not much, but a bit. Okay. If you use the delta is epsilon 2 minus epsilon 1. All right. And then if we plot, sorry, well, wait a minute. Okay, so the second one, B, we want to calculate CV. CV is partial U over partial T at constant V, right? So we just do the differentiation for that. We need to do a differentiation for this. Okay, this is easier. Okay, this is easier, not this one. Okay. Okay, so we do differentiation. We can have NK epsilon 2 minus epsilon 1 kt square, sorry, exponential epsilon 1 minus epsilon 2, sorry, 2 minus epsilon 1 kt, and oh, it's long. 加油 exponential minus epsilon 2 minus epsilon 1 kt and square. Okay, so as you can see, if we said this one is delta, we have this one delta, this one is delta, this one is delta. Okay, so easier to make it easier. Yeah, just like that. Oh, yes. Okay, so just put the pink highlight for the delta. All right. Right. Then, if we have a CV, we can examine. We can plot it. Okay, we can plot it because the temperature can be changed, right? So we can plot the function. It looks like the curve looks like in this figure. So he said it said examine the low temperature and high temperature behavior of CV and K, and sketch it as a function of KT delta. Okay, so this is the KT delta, and this is the CV divided by NK. If we do the Excel, okay, we just plot this into the Excel, and you can get this value, this curve. Sorry, this curve. All right. So which means that in the low temperature you can have almost zero, close to zero, but in the high temperature it's still going down. Why? Well, that's because you only have two energy level. Typically, the CV for this is not like that. It should be like something like that. Okay, in the real world, it should be looks like that. But this part is because they have more energy level later, and energy level 3, 4, 5, 6, 7, blah 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 blah. But now we only have two, so the effect of the two for the CV, the contribution of two energy for the CV is only like this. Okay, in the higher energy, temperature getting higher and higher, the two energy level doesn't give us really big contribution for the CV. Okay, so this is a really interesting toy model. And also, yeah, this tell you this is a toy. Okay, this is not real world looks like. The real world should be looks like this because this part supported by other higher energy level. Okay, that's it. 好，我们这是一个例子，有 n 个 distinguishable particle，那它就是所谓的波斯曼 statistic， 然后它给你一个温度，它只有两个 energy level epsilon 2跟 epsilon 1，epsilon level 2会比较大。然后呢，我们算我们的 n1 n2 很简单啦哈，就直接带这个公式就好了。那这个 n1 就等于 n 上面这个东西，然后G1 G2 会相等哈，所以它就可以消掉。那下面这个东西叫做 z 就是 sum over state。那你看我们这边有几个几个 state， 两个而已，所以我们就是两项加起来就好了。当然了，真正的世界这只是一个玩具而已，玩具模型。真正的世界它有很多个 states， 所以这边不可能只有两项哦，真实世界上。那 n1 n2 那就是把它写出来就可以了，简单。那还有你算 energy U， 好，那 U 就等于 epsilon I 乘上 Ni， 那所以就把上面这个东西就这个东西乘上 epsilon 1， 然后加总起来就可以得到这个式子。那下面这个东西其实没什么了哈，只是纯粹把这个 epsilon 不是讲错了 delta， 把它改成变成epsilon 2减 epsilon 1改成 delta 而已，就写成这样，其实没什么，这没什么用。那接下来呢，如果有 U 的话呢，它就会第二个就叫我们算 CV， 就对这个东西做微分，微分算出来以后答案就是这样子。 然后跟上面是一样的，然后我们可以把它 epsilon 2的地方写成 delta， 就这样写完了。OK， 这都没什么问题，但是接下来画的才比较有问题哈，比较有重要性，就是把 CV 画出来以后，我们就从低温到高温把它画出来。如果用 Excel 把它放上去，把它画出来，带入一些值把它画出来，我们就会发现它的值是变这样子。CV 就是一开始很低，然后越来越高，越来越高，然后怎么会又它降下来了？其实这样是不对的。真实的世界上的话，它应该是这样子的。OK， 那为什么后面这个会掉下来呢？原因是因为后面只有两个 energy level， 后面的都不见了。那真实世界上有后面那几个 energy level 就会让它变得持平，这样子，后面就会有它的功用。所以我们可以看到两个 energy level 的对于 CV 的贡献，在温度不同的状况下。这只是一个玩具，让你看看它到底有什么样的状况。Interesting. Next, let's talk about Fermi direct. We need to consider the behavior of the particle. So the particle is identical. So which means that they are indistinguishable. The biggest difference, indistinguishable. Okay. So this is the biggest problem, biggest difference between the solid or liquid Boltzmann distribution. Now we are talking about Fermi direct distribution. The Fermi direct fermion has identical particle, indistinguishable particle, and also Pauli exclusion principle. They won't share the same degeneracy with others. Okay, the fermions like electron, neutron, something like that, useful for studying free electrons in metal and semiconductor. Yeah, of course. Fermion, the famous example is electron and neutron, right? So they will, against each other. So they occupy space with the volume. Okay, so now let's talk about how we put fermion into one energy with such many degeneracy. Okay, so you can imagine that it actually looks like a coin tossing problem. Why? Because coin tossing experiment. Okay, because it's just like positive, head and tail. You can imagine that this is head, this is tail, head, tail. So actually, they are really similar. So we can recycle our formulation. W n factorial n1 factorial n minus n1 factorial. So that's coin tossing problem, really similar. So now we have nj, the state are occupied, just like head. And gj minus nj are unoccupied, just like tail. So it looks like wj equal to gj factorial mj factorial gj minus nj factorial. Okay, so that's the Fermi direct distribution for one energy level. 好，我们要讲的是 fermion， 它遵循 Fermi direct 的分布。那它的 particle 是相同的，也就是它分辨不出它们的差别，所以这是跟 Boltzmann distribution 是最大的差别。好，那它还有不会分享同一个 degeneracy 的的效果。它的例子最有名的例子就是它的电子啊或者中子啊，然后它们会真实的占据空间的位置，因为它们会排斥彼此。然后我们就把它放到一个 energy level 上，这个 energy level 有 gj 个 degeneracy， 我们把它放进去。那这个分布要怎么分布啊？ 其实啊，它就很像 coin tossing problem 一样，coin tossing problem 一样，它就是有 NJ 个被占据了，就好像是我们的正面。那有 GJ 减 NJ 没有被占据，就好像是我们的反面，应力的反面一样。所以呢，完全就是照我们的coin tossing problem 那时候的写下来就可以了。好 OK， so this is a level 1 energy level. I mean level J. Okay. So WJ looks like this. So the total number of microstate to a allowable configuration for WFD. FD, of course, stand for Fermi direct. WFD. It will be times all the multiplication. GJ factorial NJ factorial GJ minus MJ factorial with the multiple multiplications. Of course, now we need to maximize again natural log WFD. Okay, so the natural log WFD here, wow, looks like this. So you do this, do the natural log WFD, become that, and after the Stirling approximation, you can make the everything become easier, right? And yeah, so this is this one after the Stirling approximation, you can make it easier, I would say. Then we need to subject it to sigma Ni equal to N and sigma Ni epsilon I equal to U. So two constraint, of course. Then there's one thing we can emphasize here is Gi natural log Gi is something that we can neglect later. Okay, because when we do the partial differentiation Nj, the Gj doesn't has anything about Nj, so they are independent, right? So Gi equal to 0. So the first term, so the first term is not that important later, all right? And we do the differentiation for later, like this. Okay, so the first term doesn't make sense, doesn't have any effect on this. So the Lagrange multiplier function will looks like the button function. Sorry, I missed one word. Sorry, formulation. Well, looks like this. Okay, so everything become easier. 好，那一样啊哈，我们就把 level J 写出来以后，那所有的 energy level 就把它互乘起来就好了。乘起来以后呢 ，maximize 它，我们还是要 maximize natural WFD， 因为它都是用相乘的嘛，哈，比较简单。做好这个以后，哇，写出这个式子好丑啊，那怎么办呢？没关系，我们有 Stirling approximation， 让这几个项呢有 factorial 的都变成加减这样子。好，那算出来这个简单了以后呢，我们一样要对它做 Lagrange multiplier。那这边一样是要满足 particle 的 number 是固定的，然后 energy 也是固定的一个值常数这样。好，那接下来一样就是把这个新的式子 Lagrange multiplier 的 formulation 写出来，写成这样子。那这边可以想见，就是第一项这边有一个就是可以不用管它，原因是因为等一下要做 partial NJ 的时候，I 一定等于0，因为 GI 对于 NJ 是完全没有感觉的，好，就做微分就变0了，所以等一下我们就可以继续把它做下去。Okay, so yeah, this is the this one will be do the differentiation. We'll undergo the differentiation for this, but without this one, without the first term. Okay, so this term with, sorry, this term is the thing here. Okay, how about just make it cool. This one and that one. Okay, so after that we do the differentiation and also with the Lagrange multiplier, and we do the differentiation, we can get these ugly form. But don't worry, MJ and this one can be cancelled. So after that, natural log blah 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 equal to minus alpha minus beta epsilon J. So very similar formulation can be done here. MJ GJ ratio equal to 1. Sorry, 1 exponential minus alpha minus beta epsilon J plus 1. Oh, wow. Wow. So it looks a little bit different from the Boltzmann distribution. So if we want to do MJ over GJ compared to U, NJ over GJ compared to N, try to solve the alpha and beta. Unfortunately, because the plus 1, it doesn't work at this moment. Okay, so that's bad. But so for now, please trust me, and we set again alpha equal to mu kt and beta equal to minus kt first. Okay, I will explain this later. Explain. 写错字。explain later. Okay, we'll explain later, and just set that. Okay, we accept at this stage, and we can have Fermi direct distribution looks like this. Okay, we have plus 1 under here. 好 ，Fermi direct 前面的那个蓝色的部分，第一项跟微分是这个微分是没有用的，所以我就把它省略掉了。然后呢，来做微分，然后等于0嘛哈，然后就长长的东西消掉以后，然后得到NJ over GJ 1除以 exponential 这个东西加1耶，哇，加了一个1就变得很麻烦了，这造成我们 GJ 乘过去，然后想要跟那个 U 啊 N 啊来去比较，然后得到一样的答案，想要算出 alpha 跟 beta 就没有那么简单了，就这次就不 work， 可能怎么办呢？那没关系，我们就先设定说 alpha 会等于 mu kt， 然后 beta 等于-1 over kt。这个东西我们是先假设了哈，也不是假设，我们应该说先知道答案，我们先放上去哈，之后我们再解释。好 ，we will explain this later。然后这就叫做如果是 Fermion 的话，它就会遵循这样子的分布，去让它的机会是最大的。OK。Right, so next let's talk about the Bose-Einstein distribution. Bose-Einstein distribution. Again, the particle is identical as well. Of course, they are indistinguishable. Okay, and do not obey Pauli exclusion principle, so they can share the same degeneracy. That's good. Boson, for example, like photon, so it's just like light. It won't occupy the space. That's good. So they have different behavior to the fermion. So we need to treat the degeneracy, the how many ways to get the to put the particle in the energy level. We need to choose different way to see it. Okay, so we can imagine that this is a partition. This is a bookshelf. This is a bookshelf. A lot of book. Okay, so there are some partition between the books. Okay, so you can put 2 books and 1 partition, and 1 book, 1 partition, or no book between partition. So you can just choose, because when you have a range between 2 partition with the same particle books, okay, so which means that they share the same degeneracy. Okay, so you can imagine that if the GJ equal to 9, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 degeneracy, but you only have 8, 1, 2, 3, 4, 5, 6, 7, 8 partition. So your partition is GJ minus 1 partition, and you have NJ book or particles. You need to arrange the books and the partition in that shelf. How many ways to do that? So how many ways? So we can regard this question become how many ways that you have NJ plus GJ minus 1 be arranged into GJ minus 1 lines or walls or partition, and NJ particles. Okay, so WJ equal to MJ plus GJ minus 1 factorial, MJ factorial, GJ minus 1 factorial. So that's how we arrange partitions and the books in a bookshelf. So that in total, MJ plus GJ minus 1 stuffs in under the shelf, and we need to arrange GJ minus 1 lines and NJ particles, NJ books. Okay, so that's how many. 好，那我们现在讲的是下一个玻色子哦，那它是 follow Bose-Einstein 的，它是遵循Bose-Einstein 的分布。当然了 ，particle 是无可分辨的，它可以跟别人分享同一个 degeneracy。然后例如说，它的例子就是光，那光就是不会占据空间嘛，对不对哈？好，然后呢，我们来想象一下，这是一个书架，然后呢，我们可以放书跟就是小书架在那个间隔啦哈，墙壁之间，那就是等于是说，如果今天有9个 degeneracy 的话，我们其实只有8个墙啊，8个墙去分开它们，那所以就是 GJ 减1个墙，然后有 NJ 个书要放在上面，那总共会有多少东西要在上面被放呢？有 NJ 加 GJ 减1个东西要在书架上被排列，然后呢，其中有 GJ 减1是 line， 然后有 NJ 是 particles， 那算出来以后就是 WJ 会等于这样子，好，就是一个 level 它就会有这样子的排法。Okay, next level J equal to this, and then we times all together. So we have WBE, Bose-Einstein thermodynamic probability, is a multiple multiplication of this. Okay, of course, again, we are going to maximize natural log W B E. Okay, and we do exactly the same thing. Exactly the same thing, right? Yeah, nothing to say. 好，总之就是一个 level energy level J 写成这样子以后，同乘全乘起来一样要 maximize natural log W B E， 就这样啊，做一模一样的事情。And the Bose-Einstein distribution looks like that. And again, we can cancel each other like this. And then you can get this equation. Okay, one thing is really interesting here is that actually you notice MJ is a big number, right? GJ is a very even bigger number. How about 1? So small compared to MJ over GJ, plus GJ. So it can be neglected. Okay, so this is the only difference. So NJ not divided by GJ equal to 1 exponential minus alpha minus beta epsilon J minus 1. Okay, so Fermi direct, you get +1. And Bose-Einstein, you got -1. Similarly, we set alpha equal to mu over kt, beta over equal to 1 over kt minus. So you have Bose-Einstein distribution like this. Okay, so that's it. 然后讲一下，就是完全做一模一样的事情啊，一模一样的事情。然后你会得到最后这样的结果。那这边有一个小小的地方不一样，就是我们发现 NJ 加 GJ 减1这个东西，这个减1相对来说 NJ 超大 ，GJ 更大，所以这个 -1 根本就是完全可以忽略，所以就忽略完以后得到这样子的式子。那这个式子这边是减1，跟前面的 Fermi direct 是加1不一样。OK， 好，然后呢 ，So next I'm going to introduce Maxwell-Boltzmann distribution. This actually is for dilute gases, or we can say ideal gases. All right. And then in that case, remember what we do the ratio in the last example. We said GJ in the 1 liter helium, right? Remember that this is dilute gases. GJ is much greater than NJ. So when you talk about dilute gases or ideal gas, all we need to do is calculate to make the GJ much greater than NJ. If we set up this assumption to Fermi direct Bose-Einstein distribution, they will all result in the same thing, and they will become Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution is ideal gas behavior, dilute gases behavior, and we will talk about this next week. All right, so thank you very much. I will see you next week. Thank you. Bye bye. 大家再见，谢谢大家。